This is problem 4-9E. It's on page 232. Figure P4-9 shows the end of the vertical shaft for a rotary lawnmower. Compute the maximum torsional shear stress in the shaft if it is transmitting 7.5 horsepower to the blade when rotating 2200 RPM. Specify a suitable steel for the shaft. Now, if you look at the top of the next column on the page, you might be a little bit confused. The section breaks there, and so actually the only remaining portion to this problem is the figure itself. And notice that the figure has the blades attached with a collar, essentially. It's part of the mower blade. There's a key seat beneath it, as well as a step in the shaft, both of which can provide stress concentration. But then there's a retaining ring below the blade set. The retaining ring section is not really important. The stress concentration there doesn't matter because there's no torque in that section. That's below the level of the blades, and all the torque would be used to drive the blades through the grass as the mower cuts. So the dimensions are given there on page 232. You should definitely reference the figure so you understand the solution. Okay, so let's see, this is problem 4-9.E. And of course we're given figure P4-9, but also the amount of power in the problem statement was 7.5 horsepower, and the speed was 2200 revolutions per minute. We're supposed to find the maximum shear. To do that, of course, we'll have to calculate it based on stress concentration. So the maximum stress, the maximum shear stress, would be the stress concentration factor multiplied by the nominal stress. We've got a small problem here. We've already eliminated the ring. We know that that's not going to cause stress concentration because there's no torque in that section. But we don't know which is going to cause more stress concentration. Will it be the step in the shaft, or will it be the key seat? Well, the stress concentration factor, KT, for the profile key is given in the text as 2.0. That's just what we always use. Now, is that accurate? You can make an argument that you should use some other numbers too, or depending on the geometry of the key, you could use a different number, but that's what we're supposed to use, so that's what we'll do. At the step, however, we'll have to compute the ratio of the radius of the step to the diameter of the smaller section. So that is 0.05 inches. The smaller section has a diameter of 3/4 of an inch. This comes out to 0.06, and it repeats forever. We also need the ratio of the larger diameter to smaller, so that's 1 1/4 over 3/4. That comes out to 1.6. The 6 repeats forever. And we need to take these two pieces of information and look in the appendix. In fact, it's appendix A-227. If you go and look at it, what you'll do is you'll use R over dg for the x-axis and d over dg for the particular curve, and then you can read off the stress concentration factor. When I did that, I got a stress concentration factor of about 1.54. That was the most accurate I could read it off. Now notice that in order to calculate, now that we've got the stress concentration, in order to calculate the maximum stress, we'll have to have the nominal stress, and the nominal stress is just the torque over Zp, and I can never remember the name of it. When I learned this, I used J instead, but you can put the ratio of C over J together, which J is the polar moment of inertia. You can put that together into what your author calls Z sub P. It's convenient. I just haven't learned the name of it yet. I'll get it eventually. So we need diameter cubed over 16. Well, that's the same thing as 16 in the denominator of the denominator is the same thing as 16 in the numerator. So we're doing pretty well, except we need this torque. We also have to decide which stress concentration factor to use. Well, we did all this work. I'm not going to use that one because this one's bigger. So the stress concentration factor of 2 is what I'll use. We go ahead and start plugging things in. 2, well, we're stuck. We need the torque, but let's look at this just a little bit further. What diameter should I use? Well, I got this equation from the back of the book where I found the stress concentration factor. And notice that the stress would be highest even though we're not using that, the stress would be highest in the smaller section because it is the smaller section. It's the smaller diameter. And the smaller the diameter, the higher the stress is going to be for the same torque. So, so I need to use the smaller diameter. Here's the short version. It's 3/4 of an inch. It needs to be cubed. Now we actually need the torque. Of course, we'll get the 16 in there. May as well go ahead and write that down. But now I need the torque for sure. So how do we calculate torque? Well, we have power and speed. The relationship is power equals torque times speed over 63,025. Remember, the 63,025 is a conversion factor, so that we can plug the torque in inch-pounds force, the speed in RPM, and get power out in horsepower. That's what this number does for us. So let's rearrange it just a bit, because what we really want is the torque, and so that would be power over speed multiplied by the conversion factor. So plug in 7.5 horsepower over 2200 RPM, 63,025, and the torque we'll get out will be in inch-pounds. When you do that, you get about 214.86 inch-pounds force. So there's the torque we need here. Let's plug it in, 214.86 inch-pound force. Notice what happens to the units. One of the inches down here, there's 3 of them, one cancels here, and so we end up with pounds force per square inch, which is PSI, which is what we would expect for a stress. In fact, when you run all the numbers, you find that the maximum stress is about 5,188 PSI. Now we're not done. We can't just go find a material. Oh, by the way, that's what they asked us to find, that's one thing. We can't just go look for a material that would accept that much stress. Why not? Well, the mower's going to drive these blades through a lot of things, and probably going to hit a stick, maybe even a rock at times, and that's going to be an impact loading. So we need to include some factor for that, some factor of safety. So since it's impact, I would suggest that we use a safety factor for impact. In other words, take the yield strength and divide it by 12. So we'll only use 1/12 of the stated yield strength of the material. In other words, the required yield strength will be 12 times this stress. So if you take 12 times the stress of 5,188 PSI, what you'll find is that you need a material that can take about 62,250 PSI. And now if you go to the back of the book, you'll find that 1020 cold drawn, according to this book, can take has a yield strength of 64 KSI, so 64,000 PSI, and that of course is more than the 62,250 required. So here's the maximum stress, 5,188, but with a safety factor we're going to choose a material that can take at least 62,250 because of the impact loading on the blades.